Hi, good morning. My name is Azif Abdul, and this is Unit 19 Electrical Devices and Circuits. In this presentation, I will review and reflect on my work developing asynchronous counter and synchronous counter and copy machine error during my Unit 19 lab work. I'll use the plan, do, and review structure from Appendix 2 to explain what I was asked to do, how I carried out the task, and what I learned, and how this experience improved my technical and professional skills as a junior technician. As you can see, my aims and objectives are to demonstrate consistently good technical understanding and analysis of electronic circuits, including the application of relevant behaviors and general engineering skills to a professional standard, to recommend improvements to developments of the electronic circuits and to the relevant behavior applied, to explain how health and safety, electronic, and general engineering skills were effectively applied during the development of circuits, to explain how relevant behaviors were effectively applied during the development of circuits. Logic gates are tiny electronic switches that make very simple decisions using zeros and ones as their outputs. They take one or more input, and in engineering language we call them as bits, and they give out one output based on a very fixed rule. The high output are known as ones and the low ones are known as zero. Logic gates are used everywhere and to the minute devices like printer, tube lights, and even mobile phone. When a printer detects a paper jam, it sends out signals indicating it, and these are all done by logic gates. The most common and used logic gates are AND gate, NOT gate, and OR gate. Each gate has its own unique rule for how the output is designed. The output is basically depends on the input. Usually, this is all described in truth table, which lists all possible combinations and corresponding outputs. A copy machine error has three inputs P, Q, and R. As you can see in the picture, P is right P is right behind a feeder tray sensor that detects if there is no paper. S is an output gate. This blinks or indicates when there is a paper jam in Q and R gate, or if there is no paper in P. These are the evidences I took from in the lab for copy machine error. The left picture indicates a breadboard that shows wiring and a signal 100. The middle one shows truth table, which indicates the 3-bit counters, 3-bit truth table with all the results. The last one shows me trying to understand this breadboard. Asynchronous counter. Asynchronous counter is is a counter where the clock is applied only on the first stage. This right here is a perfect example of asynchronous counter, where you can see the clock is applied only on the first stage and the output is carried to another clock and another clock and another clock until it's reached its end. These are the evidences of me trying to understand this asynchronous counter in a breadboard. As you can see, there are a lot of wires, and it is compared to what the picture shows. It is very easy and very simple to make asynchronous counter. This is the reason why asynchronous counter are mostly used in small engineering companies. Synchronous counter. Synchronous counter overcome the disadvantage of accumulated propagation delays, meaning in asynchronous counter there is a small delay in real-time hardware where they tend to lag on high frequency, in which synchronous counter overcomes it. But generally uh, they are more unique, and they are more like they need more circuit wires. This is the evidence of lab evidence of me trying to understand the hardware of synchronous counter. Plan strategy. What was I asked to do? I was asked to design, simulate, and practically test an asynchronous ripple counter, a synchronous counter, and a copy machine error using flip-flops in the case of asynchronous and synchronous counter, and using logic gates in copy machine error. Both counters, in case of asynchronous and synchronous counter, both counters needed to count from 0 to 7 using 3 bits, meaning 3 inputs. I was required to explain on my performance, behaviors, and learning during the process. Success criteria. The success criteria were that both counters must count correctly and reliably. For asynchronous counter, the clock signal was little bit ripple. It was rippling through each flip-flop, which naturally introduces a delay. But for synchronous counter, the all flip-flops are must be triggered by the same clock signal so that the output change at the same time. I must apply health and safety, time management, and communication skills. I must reflect, I must reflect on what went well, what didn't, and what I have to improve. What am I learning? What was I learning? And why was it important? I was learning on how digital counters behave differently in theory, in simulation, and in real life hardware systems. This is very important for engineering students like me because counters are used in real life applications such as digital clocks, timers, control system, where timing accuracy is very crucial and very critical. One mistake can cause a very huge damage. How did I connect theory, research, or research to this task. Before building the circuit, I reviewed the theory of flip-flops and the binaries counting and applied this knowledge by designing the counters in simulation. This allowed me to predict how the output should behave and would behave, and this also reduced the error during the practical stage. How and when did I observe the observations? I recorded the observations during the simulation by pausing them in asynchronous counter, by pausing them in the simulation and taking evidence. Same goes for in hardware. In hardware, as soon as the output was shown, I recorded the evidence. Same goes for sync counter, async counter, asynchronous counter, and sync counter, and for copy machine print. How did I identify my mistakes and fixed them? When recording my observations, I recorded my observations during both simulation and practical testing. So when the counters did not operate correctly, as I was shown in the real practice view, I quickly identified my faults by checking the wires with the power switched off, verifying the clock, resetting the connections, comparing the circuit to the real life circuit that was shown to me by the teachers. This systematic approach helped me to correct wiring uh, errors and eliminate all the glitches. Reviewing strategy. What does this link prior learning? This activity links to earlier learning on logic gates, which are the base of this whole observation. Flip-flop operation, which are also a part of base. Binary counting, and which is very important during the engineering. It helped me understand the how simple logic gate concepts are and how they behave very differently in a real hardware compared to theory. As for the health and safety were applied in real life in real-time hardware by using very low voltage power supply, checking the connections before power on, and keeping the workspace very organized and clean. Time management is very important in simulation, construction, and testing, which should be completed within allocated time, which I did. Communication skills were used by fellow technical documentation, asking for guidance and when faults occurred. Skills I used and I developed. I used skills such as circuit construction, schematic interpretation, and safe working practices. I developed new skills by troubleshooting, fault finding, meaning finding faults in my circuits, and comparing my theoretical knowledge, the simulated knowledge, and measured knowledge that I measured in real-time hardware. This allowed me to learn new skills accordingly. What informed choices did I make from my reflection? From through this reflection, I learned that asynchronous counters are simpler, but less reliable at very high speed or frequency due to the propagation delay. It also it also wears out very easily. As for the synchronous counter, they are much more complex, but they offer very great accuracy, and reliability in longer term, which is why most of the synchronous counter are preferred in professional digital systems. For example, like a laptop. How will I use this in future work? Because I am planning to be a mechanical engineer, this experience will help me to improve my planning and testing strategies in future tasks. The skills I developed will be useful in further studying and in real engineering roles, particularly in systems involving timing and digital control. This will help me to understand how the the logic gates, how the binary counting is very useful. This will also help me to understand binary counting is binary counting. This will help me to understand binary counting is used everywhere. In conclusion, what went well? Both counters worked and met the success criteria. What I could have done better: wiring efficiency and speed of finding the faults. What I had do differently: m- doing more structured testing and recording of evidences. Thank you very much.